Alright, so now we're going to take a look at the last examples in the 4.3 section packet to kind of review both the increasing decreasing test and the first derivative test for local or relative extrema. So basically we're going to take a look at, we've got two parts to this. We've got one function here that we're going to find the relative extrema for. And again, as soon as you see that it's relative extrema, you know that we're going to be either discussing the increasing, decreasing, or first derivative test, not the extreme value theorem, which is for global extrema or absolute. All right, so let's take a look at A first. So our test, both increasing, decreasing, and for relative extrema, is to find the derivative. I might take my A and rewrite it in a nicer form. This is equal to k to the 2/3 times 2k minus 1, and I actually do not want to use product rule, so I'm just going to distribute this through to make my life a little easier and end up with 2k to the 5/3 minus k to the 2/3. Now before I take the derivative, I'm going to make a note to myself that we have a cusp or vertical tangent alert on this one because we have that odd root in there. So we are going to be worried about critical values where the derivative may be equal to 0 and does not exist. So we also probably want to think about our domain on this. Odd roots are always defined, so our domain is going to be negative infinity to infinity, and t is continuous. So that's also something important to take into account when we go to run these tests. All right, so now we're going to take our derivative, t prime of k, and use that to find our critical values using the easier version, using the power rule. So we end up with 10/3 k to the 2/3 minus 2/3 k to the negative 1/3. Because I know I'm finding critical values, I am going to factor this, put it in a nicer form. I can pull out 2/3 and k to the negative 1/3. We take a look at what's left. We should have a 5 left here, and then subtracting your exponents, that would give us a k. And then here we took the 2/3 k to the 1/3, so we just have a 1. So what we're really looking at is 2 times 5k minus 1 over 3 cube root of k. So as we've seen before, our derivative, finding our critical values, equals 0 when k equals 1/5. And our derivative is undefined, equals dne, when k is equal to 0. And since k t of 1/5 existed, and t of 0 existed. I don't really care what they are. The fact that they existed on the original one makes those critical values. So I'm going to create my sign chart, and I'm going to put my 0 and my 1/5. We are going to make sure we label well. This is going to be the derivative of k, which is dne for 0 and 0 for 1/5. I'm going to pick test values to plug in. So we'll pick something like 1, which is going to end up being positive. If I pick something like 1/10, 1/10 of 5 is going to be a half minus 1, so that'll be negative over positive, so that will be negative. And then pick something down here like -1, so we'd end up with a negative and a negative overall, which is positive. Then I use my derivative information, my signs of my derivative, to make a conclusion about what t of k is doing. So I'm basically determining the increasing decreasing test. So I know that we're increasing, and then it's decreasing, and then it's increasing. Okay? Now, because t of 0 existed and t of 1/5 existed, the fact that this does not exist here means that we either have a cusp or a vertical tangent line at that location. And because it's going from increasing to decreasing, most likely you're going to have that cusp or corner point that's going to be there. And then we have decreasing to increasing. Now, my reasoning, so remember your sign chart is not used to answer the question. It said find the x coordinates of the relative extrema. So as my answer for A, I would say T of K has relative extrema at x equal to 0 and x equal to 1/5 because T of 0 and T of 1/5 exist and your derivative T prime of K switches signs. Now that's enough just to say it has relative extrema. If I want to differentiate between which one's the max and the min, I would say that here you would say maybe that at K, and I probably need to switch that because my variables here, I realize I'm doing, undo. That was a really big erase. Let's change our erase to small. That it's K is my variable, so let's change that. K equal to 0 and K equal to 1/5. So at K equal to 0, there is a, because I went from increasing to decreasing, a relative max because T prime of K switched from positive to negative, and there's a relative min at K equal to 1/5 because T prime of K switches from negative to positive. You do want to be very careful when you're taking a look at this in your justification. Don't give the justification that there's a relative max because T of K switched from increasing to decreasing. That's not a calculus reason. So make sure that when you write your reason down, your justification, that you're giving the calculus version of the justification. I don't know why my machine's going a little crazy here, so let me undo that. Alright, so now let's take a look at part B here. Alright, so in part B, it's a very similar problem in that we have a similar function. We do have a cusp alert, so J of K. I am going to multiply this through, so I'm going to end up with 2k to the 4/3 minus k to the 1/3. Alright, so we're going to basically run through the same idea. We know that our domain here, like it was in A, is negative infinity to infinity, but I do have a cusp or vertical tangent alert. So we are going to worry about that. And we do know that J is continuous. Also important to make a note of as we are finding our derivatives. So J prime of K, we take our derivative, is going to be 8/3 K to the 1/3 minus 1/3 K to the negative 2/3. Because we're going to be using our derivative to find critical values, we're going to go ahead and factor. So I'm going to pull out 1/3 K to the negative 2/3. When we do that, we're going to be left with 8 and 1/3 minus negative 2/3 K. We took the 1/3, we cooked that away, so minus 1. So we're really looking at a derivative that's 8k minus 1 over 3 cube root of k squared. Alright, so now we're going to look at that. We're going to find our critical values. So I forgot which one I was doing. J prime of K equals 0 when K equals 1/8. And we know that J of 1/8 existed, so that's going to be a critical value. We also know that the derivative of J does not exist for K equal to 0, and we do know that J of 0 existed, so both of those are going to be critical values. Let's see if I can find myself some room here. Alright, so now that we have our critical values, we can create our sign chart. I'll slide over here a little bit. So we have our 0 and our 1/8. And again, remember, you're going to be very careful about your labeling. So this is going to be the derivative that I'm looking at. At 0, it was d and e, just like it was over there in 0. We test our values in the derivative. If I were to pick anything like -10, you would end up with negative over positive, so it's negative. If I pick something like 1/10, or let's do like 1/16 because that's easier. 1/16 would be negative over positive, so that's negative. And then anything larger than 1/8, say 1, is going to give me a positive value. So, and part of the reason why we had this example in there is you see that on j of k, what we know is that the function decreases, and then increases if we do the increasing decreasing test. So when we're looking at this, what's happening at k equal to 0, that is not a relative extrema because the derivative did not switch sign. So x equal to 0 is not a relative extrema because our derivative, j prime of k, did not switch signs. So only in this problem, the only extrema is x equal to 1/8 is a relative min, and that's because our derivative, j prime of k, switched from negative to positive. Right? Now, what I'm going to do just to kind of show you the difference between these two. So we've got this. Let's go ahead and graph these and kind of show you the difference between the two and what was happening at k equal to 0 in both cases. Alright, so I've gone and graphed both of these original functions using my calculator just to kind of show you an idea of what's happening. So over here on t of k, where we had, I'm just going to enlarge it a little bit so that you can see here, that on our t of k, at 0, you can clearly see that there is a cusp right there, that it was originally the function was increasing and then decreasing and then increasing, and the derivative at 0 did not exist because there was a cusp. Whereas over here on the second graph that you're looking at, taking a look at that one, why did our derivative not exist? Now remember, your calculator has some issues. There's not a gap right here. If you graph this on your calculator and hit trace, you'll see that you are defined here. Your calculator has issues with vertical sections of the graph. So you kind of have to assume that this is connected all the way. We have a calculator failure here. But what's happening at 0 is the function is decreasing, the original function. It has a vertical tangent here at 0, but it's still decreasing all the way down. And so when we're looking at this, in terms of if I were actually going to do the increasing decreasing test and name the intervals of increase and decrease, which they did not ask you to do in this problem, I'm just adding it in as a little bonus extra. Over here on this problem, you would say that t of k, and let me see, I'll fit it in right here, t of k is going to increase for -infinity to 0 and 1/5 to infinity, and that's because t prime of k is greater than 0. And our t of k is decreasing for 0 to 1/5 because t prime of k was less than 0. So that's what we do over here. But over here on this example, if we talk about increasing and decreasing, because j of 0 exists and it's decreasing, then we know that what's going on there, this is not a split interval. You would simply say j of k decreases for -infinity to 1/8, because j prime of k was less than or equal to 0. And j of k is only increasing for 1/8 to infinity. And again, because j prime of k was greater than 0. So that kind of gives you the difference. We're coming into, in section 4.6, we're going to talk about actually graphing these, not on a calculator, but by hand, using the information that we have. So this is kind of illustrating that for you. All right, so now we're going to take a look at the example 9. And again, we're trying to find the x-coordinates of relative extrema. So we know that we're not doing EVT, so we're going to use the increasing decreasing test and the first derivative test to find the relative extrema. Also, I'm going to simplify f of x before I start. Remember, simplify early and often. I can divide the x squared in, and this becomes negative x squared plus negative x to the negative 2, because that negative is in front. It's kind of understood to be parentheses there. And that'll make it a little easier to take the derivative. So f prime of x is going to be negative 2x plus 2, because you're multiplying a negative times a negative, x to the negative 3. And I am going to factor out the x to the negative 3 and a 2. 1 minus negative 3 is going to give me x to the 4th, negative x to the 4th, plus 1, which is really, let's go ahead and factor, 1 minus x to the 4th is 1 plus x squared, and then 1 minus x squared, which would be 1 plus x, 1 minus x, all over, put your 2 back up there, and x cubed. Now before I go any farther, let's talk about domain over here. Our domain is going to be negative infinity to 0, 0 to infinity. Okay, so f of 0 is undefined on this. That's something to keep in mind, that 0 cannot be a candidate for relative extrema because it's not in the domain. And this function f is continuous on its domain. If you remember, that just basically means this interval is continuous, that interval is continuous. The point of discontinuity is at x equal to 0. All right, so my derivative, finding my critical values, f prime of x equals 0. This has no real solutions at plus or minus 1, at x equal to plus or minus 1, and f prime of x does not exist at x equal to 0, but since f of 0 did not exist either, this is not a critical value. All right, so our only critical values are plus or minus 1. Now, when I do my sign chart for this, though, remember, a critical value is a candidate for a relative extrema. When I am putting things on my sign chart, I am going to still put 0 on the sign chart because it is going to be important, because you can switch increasing to decreasing at a discontinuity. So I am going to include that when I am thinking about my increasing decreasing test. However, I'm going to make sure I remember, put a couple stars over here, this cannot be a candidate for an extrema. So don't say that it's an extrema if it switches there. All right, so let's fill in what our derivative is doing. We know that it was 0 at negative 1 and 1, and at 0 it was a d and e. But I also know that it was a d and e for f of x as well. So I kind of make sure, again, starring that, because the common mistake that students make is they'll choose that for an extrema. It cannot be a candidate for an extrema. And then we're just going to test our values here. And taking a look at our derivative, this is positive and this positive, so I'm really only looking at this section over here. So if I pick something like negative 10, you would have negative and positive over negative, so overall positive. If I pick something out here, say 10, 10, I would end up at a positive, a negative, and a positive, so that's going to be negative. Then we check here in between, say negative 1/2, at negative 1/2, this is positive, this is positive, this is negative, so that's negative. And then if I put in 1/2, we have positive, positive, and positive, so that's positive. So you see how when we're looking at our original function, we are going to say the original function is increasing, decreasing, increasing, and then decreasing. But what we do not want to do is make a conclusion that there is a local extrema at x equal to 0, because that's going to be a vertical asymptote on the graph. You cannot be an extrema if you are not a point. So our answers to the question would end up basically just being that there is a relative increasing to decreasing is going to be a relative max at both x equal to -1 and x equal to 1, because, and remember, give your calculus reasoning, which is that your f prime of x switches from positive to negative, and f prime of x existed for these values. All right, and so that will keep you from making the mistake about the D and E. All right, now like we did before, I'm going to bring in the graph here to take a look at, because we do want to make this connection between what we're seeing on the derivative and what it is telling us about the graph. So here's our graph of this function f of x, and as we can see here, if I can just scooch up just a little bit to get my sign chart in, I'll move this back down here in a second. I just want to come up a little bit. We can see that our derivative was positive, our function was increasing until we hit -1. Our derivative is negative and our function is decreasing until I hit 0. And then you see right here the behavior that's clearly indicating that we have a vertical asymptote, an infinite discontinuity at x equal to 0, which is why it's not an extrema. And again, you might be a little, what's going on here? It looks like it stops, but remember, your calculator is going to have issues when we have these vertical graphs, extreme vertical graphs. And so I'll stick it over here. And so basically you just have to know that this actually does keep going, that there is going to be a vertical asymptote there. And we should have known that, because you got to bring everything in from pre-calculus. This is a non-removable discontinuity, which is a vertical asymptote. Now, one of the things I'd like you to do, kind of before you leave and we walk away from this set of notes, is actually, see like I've done here where I've graphed these functions on the calculator and I've compared what's happening on the function to what I see in my sign chart. I would like you to go back in all the examples in this set of notes and graph the functions on your calculator, and then compare those graphs to the sign charts and to the information that we came up with from the derivative, so that you can start making that connection. When we get to section 4.6, which is going to be on the exam, one of the skills is for you to actually sketch the graph given the information from the derivative that you're finding here, and that's sketching it without a calculator. So I would like you to kind of go back now and graph them on the calculator and make that comparison so that you can kind of have a heads up of where we're going in that section 4.6.